7.2 Part 3 Applications. You will need your standard normal table to complete this lesson. This lesson uses the methods found in 7.2 Part 1. When measuring data, X represents the actual number, the actual measurement. If someone asked my height, I would say 5 feet tall. That is X, the actual value. Z-scores are numbers that represent something's placement in relation to the mean. Remember, Z is X minus the mean divided by the standard deviation. Always round Z-scores to hundredths because of the standard normal table. Normal distributions are notated in parentheses, mu for the mean, sigma for the standard deviation. First number, mean. Second number, standard deviation. Example 1. I have always been short. One day at school, I saw someone walking down the hall that was shorter than me. What percent of adult females are shorter than me? I am 5 feet tall. Women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.8 inches. First, change my height to 5 feet to inches. There are 12 inches in a foot, so 5 feet times 12 inches in a foot equals 60 inches. Convert 60 inches to a Z-score. That means we're going to compare my height to the average. The mean is 63.6. Standard deviation is 2.8. Z equals 60, my height, minus 63.6, the mean, divide by 2.8. And round that to hundredths. Negative 1.28. After the 8 is a 5, so the 8 went up to a 9. Since it said find the percent that is shorter, we will find the probability that Z is less than negative 1.29. Using what we did in section 7.2 part 1, look up the Z-score in the table. The table always gives you the area less. For the less than questions, you only need to look up the Z-score. In the standard normal table, go to the negative Z-score side. Row negative 1.2, column 0.09, you see 0.0985. This means the probability that a Z-score is less than negative 1.29 is 0.0985. The probability that an adult female is less than 60 inches is 0.0985. Change it to a percent, move 2 places right, 9.85%. The percent of adult females less than 5 feet tall is 9.85%. Example 2. Human body temperatures for a healthy person are normally distributed. The mean is 98.2 degrees and a standard deviation of 0.62 degrees. Note, this differs from what we're taught of 98.6 when you take your temperature. There is research to suggest the average is lower than that. Currently, many places of business are taking someone's temperature before entering. Generally, we think of 98.6 as the average when someone is not sick. Does that mean if someone's temperature is 98.7, are they sick? No, somebody's regular body temperature might be a little higher or lower. A cutoff must be found that distinguishes a higher than normal regular body temperature and a temperature that indicates a fever, that someone is sick. I have a membership at ATC Gym. On their website, it says that anyone that has a temperature of 100.4 degrees or higher will not be allowed to enter. Would it be likely for someone's regular body temperature to be that high without the person being ill? What is the probability that a healthy person has a regular body temperature, not sick, of over 100.4? 100.4 is the actual value. Change to Z. There's the mean and standard deviation. So take the actual value, 100.4, subtract 98.2, divide by the standard deviation, and round it to hundredths. So Z equals 3.55. It asks for the probability that it is more than 100.4. 100.4 degrees converted to a z-score of 3.55. So we're looking, since it said more, the probability z is greater than 3.55. In the last section, we learned that for greater than probabilities, we look up the z-score in the table. You subtract that number from 1. When you look up the z-score, it always gives you the area to the left. The whole area equals 1. That's why we subtract from 1. So for the greater than areas, that's the right side, but the chart gives you the left. The left and the right make up 1. In the standard normal table, look up 3.55 for z. This is larger than 3.5, so the table says use 0.9999. That means the area to the left is 0.9999. Since we're doing the area greater, we need the area to the right. So 1 minus 0.9999. The chance that someone's body temperature, regular, healthy, not sick, is more than 100.4 degrees is 0.0001. It is highly unlikely that someone has 100.4 as a regular body temperature and they're healthy. If someone's temperature is 100.4, they are most likely sick. Example 3. SAT scores are normally distributed with a mean of 998 and a standard deviation of 202 points. A college decides that their requirement for admission is a minimum score of 1100. What percent of people who take the SAT do not meet the requirements? First, change the value of 1100 to a z-score. 1100 minus the mean, 998, divide by 202, standard deviation. Round to hundredths, z equals 0.50. The question asks to find the percent that do not meet. That means the person's score is less. Okay, so we're going to be looking for the probability z is less than 0.5. Look up in the table, go to the row 0.5, under the column 0.00, you see 0.6915. The question said what percent, so change it to a percent by moving the decimal 2 places to the right. We get 69.15% of people that take the SAT would not meet the requirement for admission. That does not mean 69.15% of people that apply don't get in the school. It means that everyone that took the SAT, 69.15% would not get in. This is probably a prestigious school that most people don't consider applying to, like Harvard or Yale. Example 4. The average number of robberies per 1,000 households in the U.S. is normal with a mean of 145, standard deviation of 23. In 1 year, Olive Branch had 91. Find the probability that a city will have more robberies than Olive Branch. Change that to a z-score, 91 minus the mean of 145. Divide by 23, the standard deviation. Negative 2.3478, rounded to hundredths, negative 2.35. Since the question said more, we're looking for the probability z is greater than. Remember, the area in the table is to the left, the whole is the right. The whole area is 1. For the area to the right, we look up the z-score and do 1 minus that number. Look up the z, go to the row in the column, and we see 0.0094. We're asked for greater than, so we need the right area, 1 minus that. The probability that a city has more robberies equals 0.9906. Probability means leave it as the decimal. Only change it to a percent if it asks for percent. Example 5, the mean cholesterol is 223 and 43.8 for the standard deviation. What percent of women have a cholesterol between 239 and 350? So we're going to convert both of those to z-scores. Subtract the mean of 223, divide by the standard deviation of 43.8. Round to hundredths. For x equals 350, 350 minus 223, divide by 43.8, the standard deviation, and round. It asked for the probability between. We converted those and got 0.37 and 2.9. So we're looking for the probability that it's between those two numbers. For the lesson in section 7.2 part 1, we found the probabilities by looking up the bigger z-score, looking up the smaller z-score, and then subtract. Because you find the big area and then take away that small area. So look up 2.9, you get 0.9981. Look up 0.37, you get 0.6443. Subtract. The chance that a woman's cholesterol level between those two equals 0.3538. Okay, remember to take the big minus the little. Probability can't be negative. Example 6. The mean resting pulse rate is 72.9 beats per minute. Standard deviation is 12.3. What percent is between 70 and 80? We convert those to z-scores. The mean 72.9, standard deviation 12.3. We're doing between 70 and 80. So take 70, subtract the mean, divide by standard deviation. Take 80, subtract the mean, divide by standard deviation. Round to hundredths. We're looking for the percent between, so we're going to be looking for the probability that z is between those two z-scores. We found the probabilities between by looking up the bigger one, looking up the smaller one, and subtracting. Look up z equals 0.58, you get 0.7190. Look up z equals negative 0.24, you get 0.4052. Subtract. Now it said percent, so change it to a decimal, change it to a percent by moving the decimal 2 places right. So 31.38% of women have a resting pulse rate between 70 and 80 beats per minute. Example 7. What if someone wanted to know the actual measurement x for a given percentile? The CDC wants to determine the temperature that represents 99.98% of normal values. What does this mean? They want to find a normal temperature value that would encompass 99.98% of everyone. Okay. If their body temperature was 99, this could be the regular body temperature. We're looking for a cutoff for determining a fever. We're looking for the z that represents an area of 0.9998. Okay, we're looking for the z-score this time, like we did in part 2 of this chapter. Look in the body of the chart for 0.9998. Since it's more than 0.5, half, it will be on the positive side. This is an exact value on the 3.4 row, the 0.09 column. So z equals 3.49. However, this is not the temperature. That's the z-score that represents 99.98% of the values. So to change it to z, we use that formula, plug in the standard deviation and the mean that we're given, multiply and add, and round to tenths. Since temperature measures use that place value. So 100.4 degrees. If businesses use 100.4 as their cutoff, that means 99.98% of healthy people have a regular temperature of 100.4 or less. It's highly unlikely somebody's regular body temperature is 100.4. If someone has a temperature of 100.4, it's most likely true that person is sick. Example 8. The systolic blood pressure of males is normally distributed with a mean of 118.9 and a standard deviation of 10.5. Determine the blood pressures that make up the middle 95%. The middle 95% means that 95% of the area is between two values. 100 minus 95 is 5%. So 5% of the area is outside these two areas. And half is on the left, half is on the right. 5% equals 0.05. Split into two parts is 0.0250 on each side. The systolic blood pressure of males has a mean of 118.9, standard deviation of 10.5. So the middle 95% split into two parts has 0.0250 on the left and on the right. Okay, so 0.0250 on the left, 0.0250 on the right, and 95%, 0.95 in the middle. So the shaded region's 0.95, and then the two unshaded regions add up to 0.5 to make one whole. Find the z-score with an area of 0.0250 on the left. Since that's less than 0.5, it will be negative. If you look in the chart, you see that this is a special one, that it is actually in the chart. Okay, and you see row negative 1.9, column 0.06, so z equals negative 0.96. Now, that's the one on the left. Using symmetry, the one on the right would be z equals positive 1.96. However, these are not actual blood pressure values. To change them to blood pressures, we change them to x using that formula. Plug in the mean and standard deviation given in the problem. So for the left side, we get 98.32. For the right side, we get 139.48. Okay, one time the left side we have negative z, and then we use positive z for the right side. We'll round those to whole numbers since that's how blood pressures are given. So 95% of blood pressures for men fall within 98 and 139. Example 9. The length of human pregnancies are normally distributed with a mean of 266 days, standard deviation of 16 days. What proportion lasts more than 271? So we're going to convert that to a z-score. You subtract the mean of 266, divide by 16, and round it to hundredths. So z equals 0.31. To find the proportion that is more, look it up, and remember that gives you the left side because the chart gives you the left side. To do the right side, we subtract from 1 because the left and the right make up one whole. The proportion of pregnancies that last more than that is 0.3783. What proportion lasts less than 269 days? So subtract the mean of 266, divide by the standard deviation of 16, round it to hundredths, so we get z equals 0.19. Okay. Now, to find the proportion that it is more, or excuse me, that should say find the proportion that is less, you look up 1.9, or excuse me, 0.19. Okay. Let me switch this out. This should say left. To find the proportion that is left, look up that z-score, and since it asks for less, that is your answer. Part C, how many days represent the 75th percentile? That means 75% is below. This time we're looking for x, and we're given the area. So 75% changed to 0.75. Look in the body of the chart. Okay, the body of the chart, remember, means these numbers here. Since 0.75 is more than 0.5, z will be a positive number. Okay, it's between those two values, but it's closer to 0.7486. So look to see what row and column it is, and that gives you your z-score. But that's not the actual number of days. The number of days is the variable x. So use the formula, x equals z times the standard deviation plus the mean. Plug in the values that we were given. So 277 days rounded to a whole number. So 75% of pregnancies last less than 277 days. How many days represents the 25th percentile? The 25th percentile means 25% is below. Since 0.25 is less than 0.5, z is negative. So find where 0.25 is in the body of the chart. It's between two values. It's closer to 0.2514. 0.25 is closer to 0.2514. Find the row and column, and you'll see that z is on negative 0.6 row, column 0.07. Z equals negative 0.67. Find the number of days. Use z equals negative 0.67. Plug in the mean and standard deviation, and we get 255 days. 25% of pregnancies last less than 255 days. That's the end.